Welcome to another Ultralight Airplane Design video from the Ultralight Airplane Workshop. This is the second video in the UWS-4 Structural Design series. In this particular video, we're working on the nose rib, and we're going to figure out where we need to put the rivet holes that connects the skin to the ribs. Now in this video, we're not going to get into the shape of the interior of the rib. That's going to be in part 2B. Right now, we're working on part 2A. But before we get into that, let's talk about our sponsors. As always, the sponsors for this channel are the patrons on Patreon. And we have a new patron, James S. He joined us at the Builder tier. And James has some questions about composite construction. So in our November hangar flying meeting that we have with our patrons, we're going to see if we can help James out. We do our hangar flying on Discord. If you'd be interested in joining the Discord, there's a link down in the description. And if you want to be a patron, there's a link for that down in the description too. There are several things that we've learned in some previous videos that feed directly into this video. For example, in the last video of this series, we talked about the Humble Ultra Cruiser rib, its design, because we're using it as inspiration for our rib. And a couple other videos. A structural analysis video, because there's a playlist for structural analysis. In fact, I'll put the playlist link up here. And in that structural analysis video, we looked at the skin compression loading, what it can handle, and buckling load for an aluminum skin right at the spar. I'll give you a link to this one when we talk about it a little more, because I actually pulled one of the slides out of there and put it in this one to talk about. Another video that we're going to be using a slide from is the UWS-4 Aero Design Part 11D. In that one, we talked about chordwise lift distribution or chordwise pressure distribution. And again, when we start talking about that, I'll put a link about that up here in the upper right-hand corner. Now here's one of the slides I pulled out of the structural analysis for skin compression buckling. So here's a cross section of our wing. You can see the shape of the ribs here, at least the nose rib. There's also a rear spar in here, which I didn't put in this drawing because I'm really, in this particular case, only thinking about the compression load of the skin here on the top of the rib. Here's a top view of it. So here is a rib. So the load that this rib is carrying is halfway to the next rib to the left and the next rib to the right. And then here's the spar in here. And these white circles are rivets. What we're trying to figure out in this video is how far apart are these rivets going to be. Now for the purposes of our analysis, we're going to assume that the loads that the skins are encountering are being transferred to the rib and then from the rib to the spar. Now it's not quite strictly true. Some of the skin loads here near the spar are going to be transferred directly to the spar. But to be conservative, we're going to assume they go to the rib and then to the spar. Now here's another slide from that same structural analysis video. What I'm talking about is this black line here is the top skin of the wing. Right here is the top spar cap. Here's nose rib, here's main rib. Here's the shear web through here. These are rivets. So we got rivets through that skin into the ribs. Same thing here. Here we have a rivet into the shear web that goes through both the flange on the nose rib and the main rib. But right in here, there's going to be a compression load on the skin. We're going to assume that the compression load here at the top of the wing caused by the main rib and the nose rib is going to go through the skin. Now it's not strictly true. Some of it will go through this flange over here into the spar cap. Some of it will go through this shear web where the main rib and the nose rib are going to be compressing against each other. But to be conservative, we're going to assume all of it's going to go through this skin. So what we need to do is figure out what the distance between this rivet that goes through the spar cap and the next one out on the nose rib and the other direction out to the main rib. How far apart can we put those and still have that skin carry that compression load? So that'll be one of the distances we're going to figure out. Now another distance we need to figure out on these rivets is out here on the ribs. Same thing on the main rib. We're going to have more rivets out here. So what's the distance going to be between those rivets? What's going to determine that distance, which is from another video I forgot to mention before. I did another structural analysis video where I did a pull test on rivets on the flange of a rib, a little make-believe rib, just see how far I can distort that or deflect that flange before the deflection becomes permanent. We're going to use the results from that to figure out how far apart these rivets should be. I'll put a link to that video up here in the upper right hand corner. In brief, there's going to be suction on the top of this rib up here. And so that suction force is going to try to lift up. That force is going to have to be transferred to the rivet into a flange on the ribs. Now, the farther apart these rivets are, the more force each rivet's going to have to carry. And then vice versa, closer they are together, the less force they have to carry. But the closer those rivets are together, there's more rivets you have to put in the wing, so that adds more work, adds a little more weight too. So we like to have those rivets about as far apart as we can get them. Now, what we want to do is consider the worst case scenario on the load on this skin. So let's talk about that. Now that brings us to another video that led into this one, and that's the chord-wise lift and pressure distribution. I'll put a link up here in the upper right-hand corner to that video. But this is a slide from that video. Actually, it's slightly different. It's been improved just a little bit. This should look fairly familiar. On the center part of the wing, or near the center, near the fuselage, this blue line represents the pressure distribution, chord-wise pressure distribution on the wing. So this is the leading edge up here, here's the trailing edge. So we had the maximum pressure up here near the nose of the wing and the least down the trailing edge. Now that condition is our maneuvering speed, V sub A, that's about 57 knots. That's at our N1 load, 3.8 Gs. And as I said, that's near the root. So our worst case condition on the pole on those ribs is going to be from the nose down here to about 20 inches back. So that's just a little bit aft, about an inch and a half aft of the spar. But then this one takes over because it's higher than the blue one. This condition is out on the aileron, about mid-span on the aileron, when we're in our dive speed with 2/3 of 3.8 Gs and with 1/3 of our aileron deflection. So that's about 8 degrees, 8.5 degrees of deflection. So in that case, we have more force from about the 22 inch area on back to the leading edge. So from back here, we consider this condition. In front of that, we consider this condition. Well, first, let's start on this skin compression buckling issue. Now, I pulled my previous calculations here for skin thickness and buckling load and put it into another chart here. So here's that chart. So with a 1 1/4 inch rivet spacing, so 1 1/4 from this rivet to this rivet and from this rivet to this rivet, since that compression load's pretty much the same between these two, I'll just use the same number for both. Using the analysis that I did, I knew that it could not handle more than 582 pounds of compression, but it can definitely handle at least 141 pounds. So if our load is less than 141 pounds, we could do 1 1/4 inch spacing, no problem. If it's somewhere in between, I'm not sure. It's somewhere in between here is the maximum that I can handle. I just don't know what it is. Using the analysis that I used, I'll have to do some testing. I also did 2-inch spacing. So that's 240 versus 55. And I also did 3-inch spacing. So it's 121 pounds versus 30. Now I went ahead and did the calculation on how much compression there really is up here. And that's this result down here. So that compression right at the top of the wing and at the bottom of the wing, it's going to be tension, is 7 to 8 pounds. Now, as we talked about in some previous videos, we want to do a safety factor of 1.5. So I have to multiply 78 by 1.5 and we get 117 pounds. So we have to design that skin to be able to handle compression of 117 pounds. So if we come back and look here, we could easily have 1 1/4 inch spacing on our rivets. So we can handle that compression load, no problem. Now the 117 falls in between these two. And it's almost the same as this one. So the 3-inch, I'm not comfortable. I don't think that'll work at all. Because I'm guessing that compression that we can handle is probably around 70 pounds, probably something like that. So that's not good enough. So what I want to do is try a 2-inch spacing and then do some testing to see if that will work. It's in between these two, kind of in the mid area, a little bit lower than midway. So I'm guessing that's going to work. So I'm going to do some testing to verify that. But we're going to try 2-inch spacing. So we've got part of our answer now. So the spacing from this rivet to this rivet will be 2 inches. And from this rivet to this rivet will be 2 inches. So we at least figured out 2 of our other rivet holes. I know where this rivet's going to be. I guess I should mention that. So in order to be able to handle about a 3/4 inch top flange, I'm going to put this rivet 3/8 of an inch from this edge here where the web is. So there'll be 3/8 from the middle of this rivet hole to this edge of the angle. So I know where this rivet will be, this rivet, and this rivet, at least in our first test article. Well, now let's work on this rivet span out here. And for those of you who are interested in the calculations, that nose rib lift, 61, almost 62 pounds per foot span. The moment of the nose rib, minus 60 pound-foot per foot span. And then the span is 14.8 inches. And that is the distance from midway from one rib, midway to the next rib. That's about 14.8 inches. Now using that spacing, then we come up with the total lift of the rib. That's 76 pounds. So that's actually going to be a shear load that's transferred to the shear web. And then we use the moment to calculate the compression load on the top of the wing and the bottoms. And so that's that skin compression load. So here's the calculation for that down here. Gives us 78 pounds. And just to be complete, I did it for the main rib and the flaps too. And one thing about the flaps loads are transferred to the wing at the rear spar through a hinge. So that means more than just that rivet bay spacing comes into account for the flap. So you actually have to take half of the flap span into account and load that into one of the hinges. And of course, those hinges are going to be placed at a rib. So those particular ribs are going to take a little bit of more load due to flaps and ailerons. You may remember from a recent video that I did, aluminum wingskin rib rivet load test, where I figured out that I didn't like putting more than 13.5 pounds of load on a rivet because it would permanently deform the rivet hole in the rib flange. But I was going to allow up to 20 pounds to just slightly deform it, which is allowed under Part 23. Now I did all my load calculations or load distribution. Now I did all my chordwise load / pressure distributions in a spreadsheet. So it made it pretty easy to also use that same spreadsheet to figure out how far apart should I put those rivets in the rib skin junction. So that's what this table here is representing. So I have a rivet location that I already know. That's going to be that rivet that goes into the spar cap. Now it's at roughly 19 inches away from the leading edge of the rib. So everything else goes from that. So the next two rivets out, fore and aft, would be 2 inches away. And that's because of the skin compression load. So I already know where those two are, 17 inches and 21 inches. But now I need to figure out what the rest of these rivets are going to be. So this column here, as you probably already figured out, this is the location of the ribs. Now this is the horizontal location. So that'd be the X direction, distance from the leading edge. It doesn't have anything to do with the vertical direction. This is the distance between the rivets, and I'll kind of ignore the rest of these columns here just to help me out in doing my calculations. But this blue line represents the loads from this blue line. I should have said blue column. And this red column is this red line here. So what I want to do is take the maximum load from this line back to here, and then from this red line back to the trailing edge. So I did all the calculations, and then this column is the max out of these two. So what I did is I just manually played around with rivet placements. So you can see I got up to just a little bit over 13.5 pounds here on this 4 rivet, and it's only 1 inch back from the leading edge. So on the next rivet back, it's 2.5 inches back, and then all the rest of these are underneath. Now I only went to 3-inch spacing on all these, and this goes back roughly to the aft spar. Now I only did a maximum of 3-inch spacing. I could have easily gone back to 4-inch spacing except for this one. These could have all gone up to 4-inch spacing with no problems, and I would have easily stayed underneath my 13 pounds per rivet. I think for now I'm going to stick with 3-inch spacing. Now 3-inch spacing is what Maury Hummel used on his ribs on the Ultra Cruiser. I decided to go a little bit closer together up here near the nose. And then, of course, right here at the rib cap. So I at least have some tentative rivet locations for the ribs. Now this is going to allow me to use the same exact rib locations throughout the wing. Now out at the tip, I could actually do a wider spacing out here on the nose because we're going to have less load out on the tip. If you remember on span loading, your span drops down to 0 out of the tip. So we could easily do with far fewer rivets out at the tip if we wanted to. But I'd like to make it a little bit easier on myself and not have a lot of different rivet spacing combinations I'm going to use. I'd like to be able to make most of my ribs the same. There'll be a few ribs that are a little bit different, but most of them I'd like to be the same. So I at least have some tentative locations for the rivets and the skins going into the ribs, but what about here at the shear web? We're going to have some rivets carrying this lift load of the nose rib and the main rib into the shear web of the spar. So there's going to have to be some rivets to carry that load. Now remember back up here where I calculated main rib lift, flap lift, and I also calculated previously nose rib lift. We're going to need those now to calculate those shear numbers at the shear web. So that's where we are here. Add in nose rib, main rib, and flap lift. And that's going to be at our maneuvering speed at N1, 3.8 Gs. So I pulled those numbers out, added them up, added in a safety factor of 1.5. That's 180 pounds that we have to carry from a rib into the shear. And that's worst case. As you move farther out on the wing, it gets less. But as I said, I prefer to use the same rivet pattern as I could. I could potentially reduce the number of rivets as we move out, but I probably won't unless I run into a weight problem. So I'm thinking of using 1/8 inch diameter rivets. So how much bearing, how much shear can those rivets handle? So let's do a calculation assuming 16 thousandths thick sheet aluminum. So hole diameter is 0.125. So that cross-sectional area of that hole is 0.002 square inches. Now the sheet metal bearing strength is 32,000 pounds per square inch. And that's assuming that our nearest edge is at least twice the diameter of our hole. We include this number, and we get that that hole should be able to handle 146 pounds of force. Well, our force is 180, so we're going to have at least 2 rivets. And then also the shear strength of the rivets are 140 pounds. So again, we're going to need at least 2 rivets. So we have other issues we need to think about on these rivets. Now we're not going to do it in this video, that'll be another video, but at least we're narrowing down the problems that we have to solve. Now something to think about is the ribs also act as stiffeners for the spar shear web. So here's a picture of just part of the shear web. So right now I've drawn this shear web as just a simple aluminum sheet, straight sheet. It probably won't be that, but keep in mind these ribs with these flanges up here riveting into this shear web helps stiffen it. This shear web has to keep the distance between the upper spar and the lower spar. Now the ribs certainly help do that, but it's really a shear web that does it. And of course the shear web carries the shear load along the spar. Now the shear web is going to want to buckle when we start putting a load on it. So these ribs have to prevent that buckling from happening. So it wants to do a waviness of this shear web. So we have to keep that from happening. So that'll probably require us to put some more rivets in here to stop that. Another thing to think about is that the aerodynamic center of the wing is not always at the spar. It could be after the spar. And I guess it could possibly be in front of the spar too. Well, that's going to impart a twisting moment to that skin, and that has to be transferred into those ribs. And so the rivets have to handle that too. And we didn't include that in this analysis. That my ribs, I have to do a calculation to make sure that my skin isn't going to buckle when that torsion load is applied. I don't think that load through the rivets will be significant. I'll probably do a calculation to verify that, but I don't think it'll be significant. Another thing we may want to consider is that a rib acts as a beam. Now we were talking about our spar where we have a shear web. Well, the rib also acts like a shear web because this skin acts like a spar cap, the bottom skin acts like a spar cap, and the rib itself acts like a shear web, transferring shear to this spar shear web. So there's also going to be some forces applied to these ribs between the spar cap and the shear web, or I guess I should say rib. At the moment, I'm not taking those into account either. So there's more we need to think about, but we at least have an initial analysis for placing those rivets, and then we can actually add some more forces in as we get to those to see if we still have plenty of margin. I think we're going to have plenty of margin. For example, most of the forces here that we've just talked about, the extra issues to think about, is going to apply shear to these rivets. The calculations I did so far on these is pull, tension on these rivets. So shear would be in a different direction. Now the rivets themselves can handle 140 pounds. The skin is 16 thousandths. Now the skin, we know, can handle a bearing strength of 140 pounds also. So that's quite a bit that each rivet can handle. So look at how many rivets we have aft of the spar. There's a lot of rivets. So 140 pounds times each one of these rivets, that's a lot of force we can handle. And in front of the spar also, that's quite a few rivets, and that's a lot of force those combined rivets can handle too in shear, so I don't think it's going to be an issue. So here's what the flat sheet would look like. Here would be the hole placement in the flanges. Now these flanges, of course, would be bent over a form to make it 90 degrees. Right now I've only got 2 rivets over here in the shear web. The shear web would also be bent over 90 degrees. Here's the bottom rivets. Here is a part in the flange I've cut out so it can make a sharper turn around the nose. There won't be any rivets there. So this rivet here is 1 inch from the leading edge, horizontal direction. And then the spacing to the next rivet back was 2 inches, and then 2.5, 3, 3, 3, 3, and then 2 from this rivet to where the rivet will be in the spar. I've only done the nose rib so far. I'll end up doing a main rib too. Let's look at a 3D image. So here is what a formed rib would look like. Now as you can see, what I'm currently planning to do on these inside flanges, they'll only be bent down about 30 degrees, or at least that's what I'm thinking of doing. A couple things I haven't shown here. I haven't shown the actual hole locations in this flange just because it was kind of a pain to do. I'll have to do that later. In fact, I'm going to end up redoing this rib. That's one of the reasons I didn't bother putting the holes in here. Another thing I haven't shown here is flutes. In between the rivet holes, we're going to have to put some flutes in here. Otherwise, this rib would have a huge bow in it after we bent the flange on the form due to this curvature. So I need to put those locations in. And there'll be flutes on the bottom. Of course, there isn't any flutes on a straight line bend. And then again here on the nose, because there is such curvature right here on the nose, I don't want any rivets, and I don't want to put any flutes in it because you'd have to flute just about the whole thing. So I'm just going to remove some material here, and we'll just do a very slight bend over here at the nose. We could probably actually remove it, but I would like to have it in there to help hold the shape of the nose. And then there's one more thing I'm thinking about that I'll show you. I'm thinking of a hybrid rib between a fully formed flat rib and a truss style. So I'm thinking of possibly put one truss piece here on the nose rib that will be riveted on. So I'd have to put a couple rivets here, a couple rivets here. So let's make that look like this. So flanges go one way. The flanges on this little truss piece here, which is basically U-shaped. Something like that. That's what I'm thinking. Now the reason I'm doing that is because if I made this truss piece integral to the flat piece and bent it over like I did all these pieces, it added a whole lot of extra material in here to put some of these rounded curves in here. Here, here, and here, and here. And in fact, these curves are probably too sharp here. I don't know that yet. That's another test I'm going to have to deal with. It's a 1 inch radius here. We're talking about using 20 thousandths thick aluminum here on the nose rib. And I think that's probably too sharp a radius. I'm going to do some testing. That's another video I'm going to do. I'm going to test how sharp a radius I could put in here on a 30-degree bend for a flange and see what's the minimum radius I can do and still not get cracks occurring in here on this radius. If I can make a small enough radius, I guess I could go back to having this be all just one piece. Another drawback to having this truss here, in here it's only just one extra piece. Back on the main rib, it could be several extra truss pieces because there'll be several bays there that I'd want to put trusses in. So it's something I need to figure out. Now, I mentioned in a previous video, I could try to make this cantilever, and maybe that will still work, but in order to do that, I probably have to make this wide piece here, this face, quite a bit wider back here, and then take it narrower as it comes frontward. So like I said, this interior is still up in the air. I don't know yet how I'm going to do it. I need to do some testing. So in this series, that will be the next video, determining the cutouts and lightning holes for the ribs. But before that happens, there's going to be some testing videos, some structural analysis testing videos. Well, guys, thanks for watching. Until next time.